Hello and welcome to the University of Windsor's Ed Lumley Center for Engineering Innovation. My name is Brian Esteban and I'm a graduate researcher in the Department of Electrical Engineering. And today I'm going to show you some of the interesting research projects that we have going on in the Center for Hybrid Automotive Research and Green Energy, also known as Charge Labs. Among some of the exciting research that we're carrying out, we have the design, development, and testing of permanent magnet synchronous, induction, and switch reluctance machines and drives for electrified vehicles, conductive and inductive charging of EVs, system-level simulation and testing of EVs. To support all of this research on electrified transportation, we have several high-power, reconfigurable, three-phase power electronic stacks capable of switching up to 80 kVA at 5 kHz. We also have a customized single-phase high-frequency inverter for inductive power transfer applications capable of switching 5 kilowatts at 100 kilohertz. To control all of these systems, we have an Opal RT hardware-in-the-loop system for quick development and implementation of control strategies from MATLAB code. For practical benchmarking, we also have a plug-in hybrid electric vehicle. While most of this equipment is used primarily for graduate research, it is also used for some third and fourth year undergraduate labs that focus on power electronics and machines. I'm now going to talk about a project that is especially close to me personally, and that is the wireless inductive power transfer system for electric vehicle charging. So as you likely know, electric vehicles are currently plugged by means of a very heavy cable or conductor that has to be manually inserted by the user. That can be very inconvenient when you think about a plug being dirty or maybe very cold. And then when you also think about the cost of electric vehicles, they're very expensive to manufacture because of the size and weight of the batteries required to make it comparable to an internal combustion engine. One way to solve these problems is to transfer power wirelessly more frequently and seamlessly so as to achieve the same goal that a conductor would. And so the way to do that is by means of inductive power transfer. And we have one such system here. It's actually a multi-kilowatt system. It has been successfully tested at greater than 3 kilowatts with 90% peak efficiency. So I'll now describe to you the components of such a system. So here on this side we have what is known as a primary side power supply, and it is essentially a power electronics inverter which takes slowly alternating energy from the grid at 60 Hertz and it converts it to high frequency energy anywhere in the range of 20 to 85 kilohertz. Then we take that high frequency energy and we inject that efficiently to this bottom pad that you see here, which is essentially a coil, a flat coil. And you can envision this as being embedded on the roadway, perhaps at a stop sign, at a stoplight, maybe at a parking spot, in the grocery store, anywhere where you would naturally park during your driving cycle. So once we have that energy here, it'll produce a large magnetic field which can then be picked up by a second coil or pad, which you can envision as being embedded or integrated into your electric vehicle. And so if you position this pad in the vicinity of this first pad, it'll extract that potential energy and it can then be used to deliver power to an electrical load or to charge the battery of an electric vehicle. So on the secondary side, which is this side, the vehicle side, we would have another power electronic circuit that will process that energy to convert it back from alternating energy to DC energy that can be used to, once again, charge the battery of the car. As you can see, everything that you are looking at was built and prototyped, designed in-house. And something that is noteworthy about this project is that it actually evolved from an undergraduate capstone project, a fourth-year project, and it became what you see today.